All right, one of the things you guys are going to definitely be asked to do is to create position time graphs and acceleration time graphs from velocity time graphs. And I'm not talking just a sketch. I'm talking a drawing. Okay, and when it asks for a drawing, it wants to be very specific that you're going to actually put some numbers on this and you actually have the right shapes. So let's talk about how we're going to go about this. So here in this example, I've given you a velocity time graph, and above it you see a beautiful position time graph waiting to be filled out, and below it a beautiful acceleration time graph being filled out, waiting to be filled out below it. So let's go through this. And first, I'm going to want to grab a beautiful pen. What color should we do today, guys? Let's go green. Buddy loves green. Now, when I am given a velocity time graph, the first thing I always do is I go to an acceleration time graph. And that is because the slope of velocity is acceleration. Now, obviously, as we go forward, we're talking more about calculus. So this is like super basic intro stuff. But if I ever say slope, I'll just put this at the top here. All right, so in the future, if you ever hear me say slope on this video or a previous video or something like that, I am talking about a derivative. And if you ever hear me say the word area, Freudian slip there, I mean integral. All right, so integration. So slopes are derivatives of the equation, and areas are the integral of the equation over a given region. So just some vernacular, maybe tossing in and out and interchanging, things like that. So again, we look at the slopes or the derivatives of these lines, and that's going to be our acceleration. So we have technically 3 segments here. So the first segment, we have we have a slope value of 0, okay? So for that first 2 sections, our acceleration is going to be 0. Now, I do recommend on the test, do not just leave this blank, put some sort of mark here. I always put a little squiggly just to make sure it's thick. So it says, yes, there is something there, because if they give you a line and you draw it and they can't really see it, you may not get credit for it. Then the second segment, there's only one slope. So even though it cuts through this 0 line of 0 velocity, it does not matter. Okay, you only have one slope, so you only have one velocity. And it's negative the entire time. Now, we want to get an actual calculation on this. Okay, so we know that's going to be a single negative number for the entirety of the time from 2 to 4 seconds. And you do not need to connect these, I don't. Then you need to, though, put a number on it. Okay, so remember, it's a slope. So slope is your change in velocity over your change in time, which in this case, our change in velocity is a negative 16 because we went from positive 8 to negative 8, so we lost 16 in terms of the numeric value, and it happened over the course of 4 seconds. So if you do that, we're going to have a negative 4 as our value here. Then the last segment, if you look, we have one last segment here. This is a positive slope, is a positive rate of change, but it's definitely smaller than the first one. Okay, and I know that it's positive the entire time. And again, we want to get the numeric value for that. So again, using the same setup, change in velocity over change in time is my acceleration. Then here I have a change of positive 8, because it's 0 minus a negative 8, divided by 6, because it goes to 10 seconds. And so then that is equal to basically 4/3. And so that's what we'd have here. All right, so 4/3, that would be our acceleration. Obviously, this would be meters per second squared as our unit, but that's what that's going to look like. Now, you can double check your work, because one thing I do want to emphasize that I have not mentioned before, and so I'm going to write this here in red because it is important. This may or may not be asked. This is not always mentioned on the AP exams, but sometimes does come up, and that is the idea that the area of a acceleration time graph is change in velocity. So if you were to go back, you can calculate these areas here that you've made, and you can then say, hey, if you look at that area, it's going to be equal to the change in velocity, and you can treat it like we've done in the past, with a velocity time graph being the area equal to displacement. So, on that note, let's go here. Because remember, if you want to go up to here, the area of a VT graph, also known as the integral of a VT graph, is displacement. All right. So this is where we're going to put just some dots. All right. I don't know why I got a Christmas theme going on here. It just kind of happened. All right. So the first region we're going to look at is this one right here. I always kind of highlight these, and then I like to just kind of put the numbers in them. So that way I guess I make fewer mistakes. So we've got one region there. We've got another region here. Another region here, although technically you can treat these as multiple or a single triangle for area. I do recommend that you put them in single points because that way you're going to have more data points when it comes to making your graph, which is going to be a more clear representation of your understanding of what's actually going on. So, for the graders. So I do recommend you treat it as two separate segments. All right, so then like I said, I like to go back and I just like to do a quick calculation, leave them in there. So we have 8 times 2, so this is 16. We've got 8 times 2 again, but we got to cut that in half, so it's only 8. So here again, we've got -8. And then for this one, what is the math for this one? 8 times 4, which is the same as 8 times 2, because we're cutting in half, so it's 16. All right, so now basically what we're going to do is we're going to put some dots. And since we've mixed the red and the blue, we're going to get purple. Because, you know, it's best to have some purple. All right, so sometimes you'll be told where it starts, okay? But for this, we're just going to assume that we were given an initial position of, say, 0. All right, but sometimes they'll say it started at 5, it started at 2, it started at -3. You would then include that. But let's just assume we start at position of 0. So the very first thing that's going to happen is we are going to go up 16. All right, so we're going to go up to 16. So let's just say it's about here. Because I'm also trying to figure out where 24 is now. That's about here-ish. All right, so we're going to go up 16, and so we're just going to put a dot right there. Okay. Then we go up another 8, because again, these are all positive displacements. These are all negative displacements. Because positive velocity, we're going in the positive direction. So then we're going to go up another 8, so that's why I put it to 24, and so that's why I want my line here. So at this point, I'm up to 24. And then I go down 8. Why did my dot disappear? Am I going to fight the computer today? I don't know. At this point, then we're going to go down 8, so we'll be down to here. And then we will go down 16, which will bring us back to where we started. So we've got these dots. Now, the next and last step is to make sure that we have not just the dots, which are the positions. We want to have the correct shapes. So let's go through and we'll do our shapes. Let's see, does the color talk to me today? Oh, we'll go light blue. All right. So here we have a constant positive velocity. So we are going to have a constant positive slope. Okay, because remember, as we go from here to here, the slope of the xt graph is velocity. All right, so the reverse is true. So my velocity is constant positive, then we have constant positive slope. Here, our velocity is approaching 0, so our slope is approaching 0. So now this is going to be a curve that's flattening off. All right, now it may not look like it, and sometimes if this happens, I would even write curve by that line, because you don't want to have something that's jarring, okay? It does not change lines from some sort of, like, for example, you don't want to go here and then do this. That is just epically wrong, and you would definitely be marked wrong for that, okay? And then we would continue on with this curve, which I feel like I need to get my pen out again. All right, and it's going to just kind of come around here like this. So sometimes I just kind of go through, try. As long as it's not jarring, then you'll be good. Wow, I'm in trouble here because this then has to transition smoothly into a downwards curve, and so it's going to look like this. And it flattens out to here. Okay, so that's what it's going to look like. So you have a line, and like I said, sometimes I'll actually mark it. If I was taking a test, you might want to like line, curve, you know, curve, obviously. And that's basically what it looks like. Okay, so key elements, remember, the area of a velocity time graph is going to tell you your displacement. The slope of a velocity time graph is going to tell you your acceleration. And so you can kind of go from there, go through the normal steps, and be all good. So hopefully that brings back some memories of the days of yore. I'll be back with another fun video on specifically this area of an acceleration time graph and how do we actually deal with that. So it'll be more interesting. All right, that's it. That's all I got. See you guys next time.